Okay, I don't get it. What'd you say again? Like, I'm just not reading that up. So maybe you can write it down. It just makes sense.
All right, here we go. Ready to roll. Okay, so we are still talking about finding solutions to non-homogeneous linear equations, and of course, the solutions to the associated homogeneous equation, when that's zero, helps us. That's a big part of it. So, if this is non-homogeneous, this function, sometimes called the forcing function. All right, so this is sometimes referred to as the forcing function. All right, so we looked at some examples last time talking about the method of undetermined coefficients. So we're going to pick up there. Let's do another example. Say we got the second order equation y double prime minus 4y equals e to the 2x. Call it 2e to the 2x. Okay? All right, so obviously non-homogeneous. Now, if we were going to use the method that we talked about last time, the undetermined coefficients, we would probably try the form of f of x as our particular function. We need to find a particular solution and append that to our general solution of the homogeneous equation, right? So we might try for y sub p. This is a particular solution to the non-homogeneous equation. And we generally try and pick the form of f of x and tack on terms associated with it, the derivatives of f of x, right? So a e to the 2x. Now, what would be the derivatives of this function f of x in this case? 4 e to the 2x, 8 e to the 2x. So they're not different from f of x. Up to a constant, they are all the same. So we don't need to tack on those terms. It adds nothing to it, right? So I don't need a b e to the 2x plus c e to the 2x. We just stop here in this case, which is nice. All right. So we choose that because this is the form of our f of x. Okay? Call this equation 1 for reference. So we can differentiate this because we're going to plug it in there. So y sub p prime is equal to what? 2 a e to the 2x. And its second derivative? Yeah, another 2 pops out. We get 4a e to the 2x. Plug those into equation 1. And we would get for y double prime sub p, I get 4a e to the 2x minus 4y, y sub p in this case, a e to the 2x, and we want that to equal 2e to 2x. Well, what happens on the left here? Oh, we get 0. So when I plug that back into the equation, I get 0. That does not equal 2e to the 2x for any choice of a. So this choice, this guess for the particular solution is no good. Okay? So this leads us to another, a second case of undetermined coefficients. So, note, we didn't actually find the complementary function in this one. The complementary function is the general solution to the homogeneous equation. But if we did do that, and normally we do that first, to find y sub c, we are looking for the general solution of the homogeneous equation, 4y equals 0. Okay? The characteristic equation for this would be r squared minus 4 equals 0, and the solutions to that? Plus or minus 2, which means that y sub c would be equal to e to the 2x or e to the negative 2x, any combination. What do you notice? That includes the form of our f of x. F of x is included in the complementary function. So one way to put that is that y sub c contains f of x. Therefore, any form of f of x or constant multiple of that would be a solution to the homogeneous equation, not the original non-homogeneous. It will go to 0 every time. Yeah. So, thus, our choice, ae to the 2x, cannot be of the form of the solution because it will go to 0. It's included in the complementary function, which means it's a solution to the homogeneous equation.
So does that mean there's no y sub p, or y sub p is included in, and therefore y sub p is 0?
Y sub p is not 0, but if you plug it into the left side of the original equation, it'll equal 0 every time because it's a solution. It'll make the right side 0. We just showed that we just showed that our ae to the 2x is a linear combination of the complementary function. In fact, it's just with c2 being equal to 2.
But then what happens? So that's
So that can the solution to the non-homogeneous, the original equation, cannot be that, because when we put that into the equation, we're going to get 0 every time. It's the complementary. It's in the complementary function.
wouldn't that make y sub p equal like 0? Or a function that becomes 0? Because if you got a particular solution.
But if you put 0, what's the second derivative of 0? 0. Minus 4 times 0 is 0. 0 does not equal 2e to the 2x.
Oh, right.
On the right side, we don't have 0. 0 would be a non-trivial solution of the homogeneous equation.
Gotcha.
Or, sorry, it would be a trivial solution of the homogeneous equation.
Gotcha.
Okay, so ae to the 2x is a solution to the homogeneous equation, not the original. So it just means that it doesn't mean that there's no solution, it just means that the form of the solution has to be fundamentally different than our f of x. Okay, this is the forcing function in this type, so it's not going to be of the form sum multiple times e to the 2x. It has to be fundamentally different from that because it has to fall outside the solution space of the complementary functions. Okay? If it's included in the complementary function, then there's no way it could equal 2e to the 2x on the right side because it will go to 0 every time and be a solution to the homogeneous equation. So in this case, and it's kind of like the case of the repeated roots. When we're talking about solutions to the homogeneous, we get repeated roots, we tack on a factor of x. We do a very similar thing here. The book, the way they describe it, the wording is atrocious, I think. So when this happens, if the forcing function f of x is included in the complementary function as a linear combination of the functions in the complementary function, then we multiply our choice of y sub p, the particular solution, by a factor of x. Just like we did when we had repeated roots, right? If we have repeated roots multiplicity 2, say r equals 2, we get e to the 2x and x e to the 2x as our two individual solutions. So we tack on a factor of x repeatedly if necessary. until our y sub p is fundamentally different than the complementary function. I'm going to say is no longer contained as a linear combination of y sub c, the complementary function. Okay? So in this example, we're not going to quit. We are going to try y sub p equals, instead of just a e to the 2x, we're going to try it as a x e to the 2x. Tack on a linear factor of x. Okay. And when we do this, and if this is still a linear combination of the functions in the complementary solution, we multiply by another x. Until this escapes the span of those functions, until this is no longer a linear combination of the functions in the complementary solution.
So if ax e to the 2x somehow was contained by the homogeneous solution,
Mhm.
would that mean that, that would mean that there would be a root of some kind in the homogeneous solution, correct?
Say that again?
If y sub p is equal to ae, if ae, if x to the x sub e to the 2x is in the original
Complementary.
complementary solution, sorry,
Mhm.
then that means that there would be a repeating root in the complementary solution. So generally speaking, would be easier to solve for the complementary solution first in
Right,
all these cases,
right.
okay?
Yeah, we will do that first.
Right.
Because we need to have something to compare it against. We're gonna find the complementary solution, all those linear independent solutions to the homogeneous equation, then make a choice for the particular solution. And if that particular solution is a multiple, or its derivatives are included in the complementary solution, complementary function, then we tack on a power of x until it escapes the sort of
Okay, got it.
scope of the complementary function. All right, so it's no longer a linear combination of the functions in y sub c. Now let's try this again. We differentiate, so y sub p prime would be, what's the derivative of this? This is a product rule. Derivative of the first times the second. The first is just a linear factor, so it's going to be a times 1, a e to the 2x, plus the first, ax e to the 2x, and times the derivative, the 2 is going to pop out. Oh, I should have left room for it. There it is, 2ax e to the 2x. And we need to find second derivative. All right, well, this one is just itself. I don't have that linear factor anymore, so it's just a e to the 2x times 2 pops out. Plus, and the derivative of this, well, we just did something a lot like this. It's going to be another product rule, 2ax, so derivative of the first times the second, it will be 2a e to the 2x, plus the first times the derivative of the second, another 2 is going to pop out, 4ax e to the 2x. Okay? We will be able to combine some of these. We're going to have 4a e to the 2x plus 4ax e to the 2x. Okay, so that's the second derivative. We want to sub y prime and y double prime into 1, our original equation. Okay, so it was of the form y double prime, right? And that is this guy, 4a e to the 2x plus 4ax e to the 2x. So it was y double prime minus. Never write pluses when you're in doubt when you have a pen. Write minus. You can change a minus to a plus. And then it was minus 4y prime, wasn't it?
I think it might be 4y.
4y. Damn it. And the prime. White out. All right, so minus 4y and y sub p ax e to the 2x. Okay? And that should equal, right? Our original equation was 2e to the 2x on the right. Non-homogeneous, that was our f of x. All right, so some things will combine or cancel altogether, won't they? 4ax e to the 2x minus 4ax e to the 2x, those are just going to go bye-bye anyway. And so we got 4a e to the 2x equals 2e to the 2x. So notice the left side no longer gets, what we say, annihilated. I love that word in math. It doesn't, the left side does not vanish. So I do have a coefficient to solve for. We solve this for a. All right, so 4a must equal 2. Equate coefficients of the e to the 2x. And that gives me what? 2/4. Yeah, a equals 1/2. So our particular solution is ax e to the 2x, we just found a is 1/2. So 1/2 x e to the 2x. Yeah? So then our general solution, remember, general solution is take the complementary function. That's the general solution to the associated homogeneous equation. Tack on that single particular solution that we found. Okay? And that serves as the general solution of the original equation. So y sub c, we already found that, c1 e to the negative 2x, c2 e to the positive 2x, plus 1/2 x e to the 2x, what we just found. Now, if we had initial conditions on the original equation, then we could use those to solve for those coefficients, c1, c2. Okay. All right, let's do another one. So this is the second case, what they call in the book, the second rule, rule 2 of the method of undetermined coefficients. All right, so let's look at another example. Say x double prime plus 9x equals 2 cosine 3t. All right, and in this case, x is our dependent variable. It's a function of t, so we got to keep that in mind. X is a function of t that we're looking for. So this would be our forcing function, f of t. Okay? So Nicholas made a good point. We generally would find the complementary function first. Right? I did it the reverse way around and put it in there and went, oh, 0 equals 2, why did that happen? So then we take a look at it. So generally we want to find our complementary function first, so we have a list of functions that we're looking at. So if we make our assumption that x equals e to the rt, then our characteristic equation becomes what? R squared plus 9, just 9, equals 0. Okay, so it looks like we're going to have some imaginary solutions. So R will be plus or minus square root of negative 9. And that is, what, I times root 9? That's 3. Okay. So then our complementary solution, and then what that means is the general solution of the associated homogeneous equation, if the right side is equal to 0, is, and if we get purely imaginary, just like there was one in the blue. Huh? Right, the e to the real part, e to the 0x, or in this case, e to the 0t is just 1. And so we just get a pure, c1 cosine, and it's not just t, it's times the imaginary part, so we get 3t, plus c2 sine 3t, okay? And then we start in with the particular, x sub p. All right, and a natural guess would be, if we guessed, y sub p equals, okay, so there's f of t. We might guess, and constants don't matter so much because we can make up for those when we solve those unknowns.
You mean x sub p?
Oh yeah, sorry, x sub p. So we might guess a cosine 3t and any of its fundamentally different derivatives. Remember we did that with an x cubed, we also threw, or x squared, we threw in an x and a constant. Yeah?
Just like, isn't that already covered in the c1 cosine 3t though?
Well, that one, but not its derivative. Its derivative would be sine, negative sine, but
Okay.
right?
Isn't that of the form?
Yeah, that's what I was
So
wondering.
that's of the form,
Isn't
is
it
the
like a
general
complementary
solution.
form?
Wait, say what?
We can already see that that's one of the forms.
It is, right. But generally, this would be the form of our guess. Now, why do I put in a sine 3t? This is the form of the derivative of f of t. We would normally do that, and if I took another derivative, it goes back to sine. So cosine and sine cover all possible derivatives of that. Okay, so yes, you guys caught that right off the bat. This is obviously covered in our complementary solution.
You're getting linear factors then?
Linear factors. But obviously covered, yes. All right. So we multiply our x sub p by a linear factor. Okay, so we take as our first guess, multiply t to both of these, and it would just be what, at cosine 3t plus bt sine 3t. Okay, all right, so let's go ahead and start finding derivatives. And I already did this in my notes. I don't want to think about all these derivatives. But we're going to have to use the product rule on each of these. The derivative of the first is just going to be, so if we broke it up using the product rule there, I'm going to have a cosine 3t plus the first times the derivative of the second. Derivative of cosine goes to negative sign, so it's going to be minus, and a 3 is going to pop out. So I'm going to have a 3at sine 3t, right? Plus, and then let's start finding the derivative of this guy. Derivative of the first, that's just going to be b sine 3t. Derivative of sine is positive cosine, so it's going to be plus. The 3 pops out, so I'm going to have 3bt cosine 3t. And then the fun part, we get to take the second derivative. Second order equation that we started with. Okay, so second derivative, well, the derivative of this doesn't have a factor of t in it, so it's just differentiate cosine as negative sine. The 3 is going to pop out. I'm going to have negative 3a cosine 3t. That one's done. Minus, I got to be careful with this minus because I got a product rule in here. First one, derivative of the first, that's going to be 3a. And derivative of sine is cosine. And it's 3 pops out, so 3 squared, look at that.
Wait.
Yeah.
Where'd you drop the t and then you derive the sign?
Oh, right, because I used the product rule.
Right.
So derivative of the first times the second.
Right,
You caught
right.
me. You caught me. Okay, you know what? That deserves a star.
Right, okay.
Okay, so we got the negative 3a cosine 3t. Yeah, I gave you guys solid reasons last time to use Maple.
Negative 3a sine 3t.
I think this is.
So minus
this is so
3a, that's staying. So derivative of the first, 3a sine 3t.
Okay, about the
Are you
cosine.
gonna have to take a Bronskin of this at any point?
No, not yet. Not yet. We'll do Bronskians later today. So that's why I thought about this once. I feel good about just going to the notes right here. So we got double prime minus 3a sine 3t minus 9a t cosine 3t. So that's the second part in the product rule. Plus 3b cosine 3t. We got a couple other terms. Plus 3b cosine 3t. Product rule on 2 of those, yeah. Minus 9bt sine 3t.
Dan,
Yeah.
sorry to do this, but the very first term should be negative 3a sine 3t.
Oh, damn it.
Start with.
No.
I'll start with that.
Okay. Yeah, that was an easy one. Negative 3a sine 3t minus 3a sine 3t. Okay, now let's hunt for there's some like terms. Negative 3a sine 3t minus another 3a sine 3t. Any more? B cosine 3t, B cosine 3t. So we got a couple pairs. So in other words, xp double prime equals negative 6a sine 3t minus 9at cosine 3t plus 6b cosine 3t. So that takes care of that one. We got that one, and minus 9bt sine 3t. Okay, so that's the second derivative. All right, so now we get to sub x prime and x double prime into, and let's call this guy equation 2 right here. So into our original equation 2. So x double prime plus 9x, so it's all of that. So we got negative 6a sine 3t minus 9at cosine 3t plus 6b cosine 3t minus 9bt sine 3t. Luckily, that's not a long equation, equation 2, plus 9x. All right, so, and x is right here. Linear factors right here. Okay, so it's going to be plus 9a t cosine 3t plus, and a 9 there, we're multiplying 9x, yeah, so 9bt sine 3t. Okay, and that equals our original equation. We subbed it into the equation 2, so 2 cosine 3t on the right. All right, so let's start looking at things that might cancel out. Anything? 9at cosine 3t, do I have anything like that? Minus 9at cosine 3t plus 9a cosine 3t. We got a minus 9b sine 9bt sine 3t plus 9bt sine 3t. Okay. So we get, let's write it one more time. Negative 6a sine 3t plus 6b cosine 3t equals 2 cosine 3t. Okay, so we have this equation involving a and b, and we need to equate coefficients of corresponding terms. So on the right, I just got cosine 3t. There's a cosine 3t. So in other words, 6b has to equal 2. And the coefficient of sine 3t has to equal, what? 0. So negative 6a has to equal 0, and 6b has to equal 2. This is our system of equations. So after all that differentiation and ugly business, at least I just got these things where, hey, a is 0, and b is 1/3. So the form of our particular solution, a is 0 and b is 1/3. A is 0, b is 1/3. 1/3 t sine 3t. Okay. All right. So what would our entire general solution look like? complementary solution plus particular solution.
C1 cosine 3t